Okay. So in ASE 7.5 or 7.10, you can see there are certain combinations for strength design and for allowable stress design. So based on that, I have prepared load combinations. Okay, for LRFD method, 1.4D, you can see here, 1.4D. Okay, that is 1.4 dead load. Okay, D is dead load, L is mezzanine live load or floor live load. You can see here, L is live load or otherwise floor live load, you can say. Okay, this L is floor live load. LR indicates roof live load. This is snow load, rain load. W indicates wind load and any other thing. E indicates earthquake load, like that. Okay, so we will not have generally all these snow and rain. If you have anything, you'll mention in the combinations. In general cases, we will not have all these things, snow and rainfall loading. Okay, so 1.4D, I have taken combinations. 1.4 dead load, that is the first combinations. 1.4 dead load. You can add collateral load in dead load also, because if you observe all these combinations, they have not given anything specifically about collateral load. Because collateral load is additional dead load, you can apply the same factor, the same as dead load. So that is 1.4. CL also you can mention here. Okay, the syntax is that 1.4 dead load 1. Okay, what is the dead load case number here? Dead load 3. If you observe load case number, what is the load case number for dead load? Load case number 3. Okay, so the 3 is here. Okay, next you have to give one space and then you have to mention the factor. What is the factor he is mentioning here? 1.4. For I have added collateral load also here, right? So for what is the collateral load case here? 5. Load case number 5 for collateral load. 5. Again, the same factor as in dead load. Okay, this is the first combination. And if you observe second combination, 1.2 dead load, that is 1.2 dead load here, and 1.6 live load. Because there is no specific collateral load combination, the same factor I have taken for collateral load also. Don't confuse. Okay, 1.2 dead load. Anywhere dead load comes, you have to take collateral load there, because collateral load is additional dead load and it acts with the dead load only. Okay, that is why there is no separate combination if you observe these combinations. So that is why you have to take collateral load wherever there is dead load. Okay, so dead load and collateral load combines the same. And the next thing, keep this aside, temperature load, and see remaining things. 1.6 live load. Live load indicates floor live load, that is mezzanine live load, 1.6 times. And the next thing, 0.5 roof live load, 0.5 roof live load. Now here the extra thing I have taken is 1.2 temperature load. Why I have taken 1.2 temperature load? If you observe all these combinations, there is no temperature load combination specifically given. But if you go through the class 2.3.5, there is something written here. Wherever applicable, the structural effects of load T shall be considered in combination with other loads. Okay, the load factor on T shall be established considering the uncertainty associated with likely magnitude of load, the probability that the maximum T will simultaneous with other applied loadings, the potential adverse, something like. Okay, the last point, if you observe here, the load factor on T shall not have a value less than 1. Okay, so anything, any value, any partial factor you have to take for temperature loading, it should not be less than 1. So what we take generally, what is the factor they are applying for dead load? They will take the same factor because it is more than 1, because it is 1.2, right? So the same factor will be taken for temperature load also. Okay, anyway, it should not be less than 1. 1.2 we have taken. It is not less than 1, right? So 1.2 temperature load. So you will get doubt, sir, why we have taken temperature load in this combination only? You can take anywhere. Actually, you thought like that, right? So why we have to take in this combination only? there is a particular reason. Okay, if temperature is more, just before that, think practically one thing. This is roof live load. What is roof live load? What is roof live load? What are the things comes under roof live load? Can anyone guess?
Six.
Since it is pitched roof, B, make sure that while you are answering this question, it is pitched roof. So now tell me, what is the roof live load? What are the things comes under roof live load? Yeah. So this roof live load is nothing but, actually there will not be any direct live load on the roof, but what this roof live load? It is the weight of a particular person which goes for maintenance above the roof. Okay, like while erection, he has to, he has to clip the purlins or clip the sheeting, or he has to go above the roof, right? In that case, or something while maintaining the structure for every year. Okay, like one person goes above the roof and he will maintain, or he will paint the particular steel or something above the roof, anything is there. He'll maintain for maintenance purpose only. One person will have to go above the roof. That is generally 60 kg per meter square on an average they will take. Okay, that is the pitched roof live load. Okay, so directly you can think that this live load is load of a particular person which goes above the roof for a maintenance purpose. Okay, sometimes in some areas there will be sand load. Okay, sand load which also acts under live load, but most of the cases customer will not provide any sand load. Okay, generally sand load where there is heavy dunes, etc., where there will be heavy dunes, sandstorms, etc. So that sand will be deposited over the roof. That comes under live load cases. But most of the cases is that it is the weight of a person, I can say. Okay, so that is why there is partial safety factor. You can see here 0.5. So we are not applying full roof live load. Okay, there is reduction of roof live load here. So practically, if the temperature is more, so any person wants to go over the roof for maintenance. If temperature is more, nothing but if you see in the summer season, if it is afternoon, any person wants to go over the roof for maintenance? My voice is audible to all of you, right?
Yes, sir.
Yes, sir.
Yeah, right. So in the summer season, generally, why I am taking summer season? Because we are applying temperature load. Temperature will be more generally in our climate changes. So temperature will be more in the summer season. So in the mid or in the noon. So any person wants to go over the roof for maintenance in the noon?
No, sir.
No, right, exactly. So there will be less live load. And there is no wind load. If there is full wind load acting on the structure, any person wants to go over the roof for maintenance? No.
No.
Okay. So in that cases, that is why practically they have chosen this case for maintenance. Okay. So 1.2 dead, 1.6 mezzanine live load. This is not in our case. 0.5 live load, because there will not be full live load when temperature is there. So that is why we are considering temperature here. Is it clear to all of you why I am taking temperature load in the combination 2 only? Clear?
Clear, sir.
Fine, thank you. So that is why I have taken temperature load here in the combination with the factor which should not be mentioned, that it should not be less than 1. So it should be greater than 1. So what is the dead load factor? Practically they will be take, okay, like this. Okay. So this is all about taking things. Okay, 1.2 dead load. So 1.2 is the factor, dead load case is 3. So the next thing is 1.2 collateral load. 1.2 is the factor, collateral load case number is 5. Okay, that's why 5 space 1.2. And 1.2 temperature load. 1.2 is the factor, temperature load case is 12. If you see here, temperature plus temperature load case is 12. Okay, and 1.6 mezzanine live load. Mezzanine load case, load 14, mezzanine live load. Okay, because we have taken like this, right? So this is dummy thing. We are not having any loads here in this case now. In next class, we will see mezzanine loads. So, but as of now, there is a combination. That's why I have taken this one. Okay, so 1.6 into dummy load 14 case and 0.5 of roof live load. 0.5 is the factor, roof live load case is 0.4. Because we are having two temperature loads. One is plus 30 and the other one is minus 30 differential temperatures. So temperature load case 1, temperature load case 2. This is the only change in these two. All the things remain same if you see. So that is why 1.2 temperature load 1. If you see, load case is 12 here, load case is 13. Load case is 13 is negative temperature. So this is the only case. Like that, you have to take combination for all the cases. If you see, suppose, if you see fourth combination or if you see third combination, okay, there is roof dead load is the only one case, roof live load is the only one case, and one case with mezzanine live load, and there are 6 cases with wind load, right? One case with mezzanine live load. If you see combination here, only one case, that is load case number 14, mezzanine live load. That is dummy in this program. It is dummy. And if you see 0.5 live load, sorry, 0.5 wind load, 0.5 wind load 1, that is load case 6. First wind load case is load number 6, right? So that is why wind load 1, load number 6, wind load 2, load number 7, wind load 3, 4, 5, 6, up to load case 11. Wind load 6 is load case 11. So all these things you have to write combinations like this. So how to write combinations clear, all of you?
Yes, sir.
Clear? Clear, fine, thank you. So this is strength combinations. If you see here, allowable stress design load combinations are there. Okay, generally these are serviceability load combinations. We can see serviceability load combinations. So it is dead load. You can see, I told you just now, one dead load, one collateral load also you can write in this session. So 3, 5, 1.0. So this is the first case, and dead load plus live load, that is the second case. Dead load plus live load in the sense floor live load. That is why I have taken mezzanine live load here. Anywhere dead load comes, collateral load comes there. So like that, one collateral load. And if you see here, dead load plus live load, also snow and rain load, there will not be there. So dead load plus live load, roof live load is there. So this is the third combination. Okay. And the next one, okay, I'll zoom in. Dead load plus 0.75, live load plus 0.75. So if you observe here, again, roof live load factor has been reduced here. So in this case only we'll apply temperature load, because that if there will be full roof live load, there will not be, if there is temperature load, if nothing but if there is much more temperature, or if it is freezing temperature, so no person will go above the roof. That is why where there is load factor less for roof live load, you have to apply temperature load. And where there is no wind case, make sure that there is no wind case. Here in this combination, you see there is no wind case and live load reduction is there. That is why you have to apply temperature load here. So why you have applied 0.75? If you see here, again, in AC designs also he has mentioned, what is that? Yeah. If you see here, wherever applicable, something, all these things. The last point, the fraction of T considered in the combination with other loads shall not be less than 0.75. That is why they have taken 0.75. Okay, it should not be less than 0.75. The minimum value is 0.75. You have to apply for temperature load. The minimum factor you have to give 0.75. That is why they have given, sorry, we have taken 0.75 for all these things. So remaining all the things, you have to do all these things. So up to dead load plus earthquake combination. So make sure that if you observe all these things, there will not be wind and earthquake acting simultaneously. So both will act, both will not act simultaneously. One case wind load is there, another case earthquake is there. If you observe here also, dead load plus 0.6 wind or 0.7 E, either wind acts or earthquake acts, like that it will be. So that is how you have to take ASD combinations. So if you are okay with writing all these things, right? How to take LRFD combinations, how to take ASD combinations, right? Syntax is, all of you got it, right?
No, sir. The
Yeah.
syntax means?
Syntax means nothing but this is the syntax. You have to write load case number,
Okay.
space, load case factor, and the next load case number, next load case factor, like that. This is the syntax I can see. This is like program, right? I can see that is syntax.
Okay.
So I'm copying all these combinations in my program, if you are okay. So copying all these things. So if you observe here, load combination 100, I have taken starting ASC 710 LRFD combination starting from 100, and it has ended with load combination 125. After that, ASC 710 ASD combinations started with 200. You can take any number, 200 or 300 or 500 or something, 350, anything you can take. That's your wish completely. Stat will not do any objection here. Okay, it ended with 228, like this. Okay, so but you have to give only particular one methodology combinations only. So that is where load list command works here. So just load combinations have been done, and the next we have to give perform analysis command. So you have to do perform analysis for all these things. Why? Because I'm taking LRFD method for design. So anyway, it has to perform analysis for all these combinations, but you have to check deflection criteria for serviceability combination. So it has to perform analysis for all these combinations. So that is why I'm not giving anything directly. I'm giving perform analysis after all the combinations. So this is change in step. I'm commenting here. And but you have to design for one methodology only. You should not design for all these combinations. Either you have to design for allowable stress design, or you have to design for limit state resistance factor design. Okay, load resistance factor design. So whichever methodology you can take, like that. So I'm taking load list command here. So load list. So I'm taking LRFD combinations only for design. So load list is from 200 to, sorry, not 200, LRFD, right? So 100 to 125. So load list 100 to 125. Like this you have to take. So performance analysis happened, load list happened. And the next thing you have to take is the parameters. Okay, design parameters. So for that we have seen how to give parameters in the beam analysis. So the same way, parameter 1 I'm taking here. And in that, what is the code you are using? So code AISC unified. AISC unified 2010. So why I have written unified here? So actual, what is the name of this code? If you observe, what is the name of this code? AISC 360. 360. Where you can use 360? 360 angle. Nothing but 360 angle is nothing but it will cover entire circle, right? In that aspect, they have written this code number 360. 360 means it will cover entire circle. So what is the angle in a circle? Complete angle in a circle, it will rotate 360 degrees, right? So that is why they have provided 360. So that is why unified name comes under here. So I'm designing AISC unified 2010, and method you have to specify whether LRFD or ASD you can take. If you take ASD combinations here, you can take ASD here. So that is how you have to take. And track. So track 0, or what is track 0? Nothing but print the output at minimum detail level, because I can check my own whether it is passing or not. It need not to show. Okay, because I can check, because if you want to give output to the customer, no need to give bending moment, shear force for every member, for it at every segment. You need not to give, right, all these things. That is internally, that is internal matters. Why you have to give all these things to the customers? Okay, if he asks anything, then you can change this value. Okay, it's your wish, completely your wish. This will not affect any design. Okay, track 0 all, and I'm using CB. What is the CB is nothing but I'll tell you. CB is modification factor for lateral torsional buckling. Generally, there is there are approximate 2 to 3 equations are there to calculate CB, but this is the lengthy process to calculate CB. If you give 0 here, that value it will calculate directly by the STAD. Okay, because our program, our method will be simplified, I can say. So if you give 0, it will be calculated directly by the modification factor. It is CB is modification factor for lateral torsional buckling. Okay, that will be calculated directly by the STAD if you give 0. CB naught and beam 1 all. What is beam 1? We forgot all these things. Beam 1. Beam 1 is nothing but it has to perform analysis. Suppose if you take member 8, what is the length of the member 8? It is 3 meters. So it has to perform analysis at 1/3 of every portion. So it will divide the entire 3-meter length into 12 parts, and it will perform analysis and every 12 parts. Okay, that is how you have to give beam 1. If this 3-meter length portion fails at any part of the beam, it will show the entire segment has been failed. So because the safety is our first priority, you have to give beam 1 command, because it has.
Sir. CB, can you explain, sir? CB 0 on.
Yes, just now I told you this is the CB is nothing but modification factor for lateral torsional buckling. If you see chapter 7, okay, so in the chapter 7 there are certain 2 to 3 equations. Okay, all this is lengthy process. Okay, but there is one command in the STAD. If you give CB 0, the STAD itself will calculate the modification factor for lateral torsional buckling of each and every segment. What is lateral torsional buckling? So I can define lateral torsional buckling if suppose, so okay, it is not showing a section here. How we can say? So okay, yeah, just give me a minute. There is one tool. So okay. So okay, if it is the I section, Lateral torsional buckling means if you observe lateral as well as torsional. Torsional means the eye section will buckle in this shape. Okay. Lateral and torsional. So if you observe cross section, if you observe longitudinal section, this is lateral. And if you observe cross section, it will be like this. Both will act simultaneously. It can be called as lateral torsional buckling generally. Okay. But there is one modification factor defined in chapter 7. Okay, there are sometimes 2 to 3 equations to calculate modification for this thing. But since it is a lengthy process, they have given one automated option. If you provide 0, STAT will calculate automatically the value. CB is nothing but modification factor for modification factor for lateral torsional buckling. Okay, 0 means it is not 0. Factor is not the 0. It will calculate directly by the STAT. Okay, so like that you will give. And beam is all you know. It will perform. It will divide the entire segment into 12 parts. It will perform analysis for each and every 12th part, so that if any part fails in the beam, it will show the entire beam has failed. That is the advantage of beam 1 command. And FYLD yield stress, you can mention as per your company norms. Some companies will give you something. Okay, whatever the steel values you'll give, the company will give you. I'm taking my default value. Okay, don't confuse with all. All is nothing but you have to apply these parameters to all the members. Okay, all is nothing but you are assigning these parameters to all the members. Whatever the member you have shown or you have provided in the geometry, you are applying for all. FYLD, yield stress of steel. And anything we have? 0, CP0. Fine. So nothing we have forgot here. So next, rafter unsupported lengths. Okay, we have completed parameters here. We have to give unsupported lengths and effective lengths, all these things. Okay.
Sir, what about ultimate, sir? It won't affect our design. FU.
Yes, of course. If company provides, so you can provide ultimate also. No problem. Sorry, how many zeros? No problem at all, because we are not doing design up to ultimate stress. We are not doing plastic analysis, right? So anything, any matter that will not affect our thing. Okay. If you give all, there will be no problem at all. If you give this thing. Okay. So the other thing is that for rafter, what is the length of complete rafter? This thing, because I am taking this thing, the bending moment diagram of the rafter will come like this for gravity loads, right? Like this. So it is obviously there is change in the segment of rafter. If you see, if this rafter is like this rafter is like this. So this rafter will discontinue here. So LZ will be 27.285. If you see here, 27.285. You'll get doubt, sir. There are some 6 to 14 members are there. So how you are giving 27.285? These are the segments. The members from 6 to 14 are the segments which I have divided for optimization only. It is for my convenience only. I have divided the entire rafter into number of pieces. Okay, but practical view, it has to act for the same length, because there is no disjoint here. There is no disjoint here, right? So it has to act for a complete length. That is why LZ is 27.285. For what members? 6 to 14 and 15 to 23. So I can say 6 to 23. Clear? Because all these are segments are made for my convenience only. Okay, clear? This entire rafter has to act as the same portion. There is no disjoint here. That is why I am taking LZ as full length of the rafter. There is disjoint here because the rafter shape is anyway changing here. That is why up to here only I am taking. So it is clear?
Clear, sir.
Clear. So I'm going to take Ly. So what is Ly? So just I'll draw one more thing for you. Yeah. So if rafter is going like this, okay. So purlins will sit like this, right? Over the rafter. Right. Purlins will sit over the rafter to support sheeting. This is what we have seen in the first 2 to 3 classes, right? Purlins will sit over the rafter to support sheeting. These are called purlins, jet sections generally. These are called purlins. They will sit over the roof. They will be connected to roof by bolts. Okay. So over that there will be sheeting. Okay. So sheeting will be connected to purlins by using bolts again. So this is how generally it will be made. So these purlins will provide support to the rafter. Okay. These purlins will provide support to the rafter because top flange is connected to this thing, purlins, right? So anyway, bolt is connected to top flange. So support will come to the top flange. So you will get doubt generally. So why it is providing support to the bottom flange? You can doubt, right? Bolt is not extending up to the bottom flange. So how it will support? There will be purlins run over length, right? Like this. Okay, in the Z direction, they will protrude out of the screen, right? Out of the screen, right? So they will provide some flange bracings. Okay, so these flange bracings will support the bottom flange at this portion. So that is why a complete purlin will support the rafter, will provide unsupported length. If there is unsupported length, the the rafter flange may buckle. Okay, but these purlins will provide support to the rafter so that the flange of the rafter or the web of the rafter will not buckle. That is why unsupported length of the rafter will be reduced to purlin spacing, whatever the purlin spacing you are providing. Okay, suppose let us take this as 1500. Okay, that is Ly. So is it clear to everyone?
No, sir.
No?
No, sir.
No means your doubts or no or not understood?
I have doubt. I have doubt, sir.
Yes, tell
This
me.
is a 150 mm. The purlin spacing is 150 mm.
I told you this is 1500, not 150.
1.5 meter.
1.5 meter.
Okay.
I'm telling you now, it is not writable here. I cannot able to write properly here. Okay, because it is drawing like this, right? That is why I cannot able to write properly here. To show you just, that is, it is 1.5 meter.
Okay.
Purlin spacing. You cannot provide 150 mm because the flange itself comes under around 65 to 100 mm. So you cannot provide side by side purlins like this. It will clumsy. It will get clumsy and it will give much more weight. Generally, if you observe the purlin weight, it will be 3 to 7 kg per meter square over the rafters. Purlin weight, if you calculate after the design, this purlin weight will comes under 3 to 5 kg per meter square over the plan area. That is how practically they'll come. So it is clear now?
Clear, sir.
So, okay. Yeah, thank you. I'm taking that supporting as 1.5. No? We have taken, yes, 1.5 for members 6 to 23. This is LY, minor axis. And what is UNT? Unsupported length of top flange.
Sir,
This is for
sir,
where?
one doubt, sir.
This
Sir,
is for
one doubt,
top.
sir.
Yes, tell me.
Sir, the purlin length, everywhere we are taken 1.5 meter or less than also we have taken.
Yes, that is very good doubt. Actually, if you observe in AISC, there will not be any provision in Indian standard, but in AISC, there will be coefficients at end portion. There will be higher wind pressure acting actually. Okay, if you see member 6 and 23, there will be we'll see how to calculate purlins. Okay, in that portion we will see at the end of the rafter there will be much more pressure acting on the purlin. That is why they will come closer here. Okay, but the purlin spacing may be increased in between the rafters. Okay, but they will come closer here at the end of the rafters. 6 and 7, remember 22 and 23. But in our design, we cannot change everything like that. There will not be much more effect like that. Okay, that's why we are giving maximum value.
Okay.
But actually, practically, the purlins will come closer here and you can keep constant spacing for this portion.
Okay, what are the spacing we have provided? That spacing only we have to take LY, right?
Yes, what is the maximum purlin spacing you are providing on the top of rafter? That is what you have to take in the design.
Okay.
Clear?
Clear.
Yes. This is support to the minor axis, unsupported length of top flange, and then unsupported length of bottom flange. Bottom flange also I am taking 1.5 because you can give flange bracing. Okay, from the purlin. If it is purlin is running like this, you can drop one flange brace. Flange brace is nothing but need not any design. You can provide some angle. Okay, some angles 50 by 4, 75 by 6, anything you can provide one angle to the bottom flange. That is how you can take unsupported lengths for the rafter. Okay, now it is for columns now. Okay, so I am assuming that I am designing it for pinned base. Generally, any structure has to be checked for pinned base for optimal design. Because if you give fixed base, foundation will be more because there will be movement acting at the foundation. You have to design foundation for fixed moments. So foundation will be uneconomical in that case. And that too you have to provide is straight members. Straight members are always uneconomical. Okay, if you give tapered members only, nothing but where there is no necessity of increasing the section, you can decrease the section. That at that time only you can give economical section. That is why always you have to try to pass the structure with pinned base. So I'm going to take pinned base in this session. So if you go to the table CA71 in the AISC 36010, so there is one table, effective length factors. Okay, so if you see all these are pinned bases, these so these will not comes under our condition, but these two are pinned bases, right? One is this one is this one. But what is in our case? If you see here, we will fix the column to the rafter. This is fixed connection here. Whatever portion I'm highlighting here. Okay, this will be fixed. This connection will be fixed. Fixed nothing but rotation will not be allowed. Okay, because we are fixing this one, rotation will not be allowed, but translationally it can be shifted or it can be displaced. This member can be displaced. Suppose if the wind is acting in X direction, this entire structure will displace like this. Okay, so there may be a chance of displacement due to the acting of horizontal loads, but you should not allow the rotation at this portion. So what is the condition we will get here? Where is that? This one. So what is the condition you get here in this D and F?
Condition is I'm not getting, sorry. Condition is the what type of condition?
D no, F no, sir. One end pinned, other end.
Yes, exactly. So someone is not getting, I'll explain you. Okay. If you observe here, one end is pinned, other end is pinned. Because we are doing pinned base, so there will be two chances of applicable conditions here. One is condition D and one is condition F. In both these conditions, only you will get pinned connection at the bottom. Okay, right? So if you take D, it is taking pinned connection at the top also. But I told you that we have to fix the rafter to the column because all the PEB connections, it is rigid frame only, right? Rigid frame. Rigid frame is nothing but you have to transfer the moment from the column to rafter. That is only rigid action comes into account. Clear? So
Unclear.
you have to transfer the movement from column to rafter, rafter to column. You have to transfer the moment. That is, you should not allow release of moment. That is why you have to fix the connection here. So, but translation is allowed. Translation is nothing but displacement is allowed due to horizontal acting of horizontal wind loads because we are providing pinned connection here. The structure may deform like this. There may be a chance of displacement here. That is why only F condition comes into our account. What is the K value here? 2. Effective length factor, it is 2 here. So you have to take theoretical value, practical value, recommended design value. Anyway, both are 2. You have to take 2 in the design. KZ value 2. So for that portion, you can mention this thing in 2 ways. One way, I'll tell you what is the height of this column. I can measure from node to node distance. 6.4, right? So LZ will be 6.4 for members 1, 2 and 3, 4. Both the columns are symmetrical, right? Members 1, 2, 4. So is there any confusion here? Why I am taking LZ, why I am taking member? Clear? LZ is nothing but length of the column. This is the value for length of the column. These are for the members which you have to apply this unsupported length, or I can say a major length. Okay. So what are the numbers of members? 1, 2 and 3, 4. This is how you write actually. But in our case, what is the KZ value? KZ is 2 for these members. You can write like this one way. Okay. But the other thing you can do is that if you're not mentioning KZ here, you can directly take 6.4 into 2. That is 12.8 you have to mention here. Clear? If you take only length 6.4, you have to take KZ bottom of the this syntax. Next to the syntax, you have to take. Okay. If you don't want to take this one into account, okay, I'm commenting this one. Whatever you don't need anything, you can comment with star. That will not comes in the design. Okay. So if that you don't want to take that line into in your design, you can directly multiply with 2 over here. Clear?
Clear, sir. I have
Sorry.
If I use any strut pipe, no, sir, then LZ will become change.
Strut pipe means generally strut pipe will not allow any bending moment. You are mentioning strut. It will not allow bending moment. It will take either compression or tension, right?
No. It's like what a tie beam type, sir. Toward along the column.
Along the column.
Or if it is LJ total 6.4 meter, no, sir. Can I put at 3.4 meter one tie?
Okay, if you are allowing a tie beam all around the structure at 3.4 meter level, so what will be the LZ value? That is your doubt?
Yes, sir. Yes, sir.
Okay, one thing you need to know, because the tie beam will be connected to the web of the mainframe column, right?
Yes, sir.
Because you are providing perpendicular to the screen tie beam, right? That should be connected to the web of the mainframe column. We cannot take these two as separate members in that case. Okay. You have to take 6.4 only in that case also. If there is one mezzanine, suppose, okay, mezzanine beam will be fixed to the column flange if it is like this, okay. In that case, it will be fixed to the beam. In that case, you can segregate this 3.4, LZ 3.4 for 2, LZ 3 for 1. Like that you can do.
Okay, sir. Got it.
Clear? Got it. Yes. This is how you will take LZ. Sorry, I'm getting late. All of you are getting late due to me.
Yes, sir.
Okay. Otherwise, shall I stop here?
No problem, sir. You can continue, please.
I can continue, right?
Yes, sir.
Yes. Thank you. Thank you very much for your support. Because all these are practical sessions, we cannot estimate the time. Because you people must have to understand, right? That is the main concept. Okay. Suppose I'm taking a grid line along 8, right? Frame along grid line 8. So what is the wall condition there along grid line 8? So if you see elevations, there is 2.4 meter block wall and above sheeting. I'm mentioning here along grid line 8, wall condition is 2.4 meter block wall and above sheeting. Here also along grid line 8, 2.4 meter block wall and above sheeting. This is our example, right? I'm taking like this. So if you observe, if I take sandwich panel or anything, any sheeting for the wall, customer has requested that I will construct one wall up to the, if I zoom in here, I will construct one wall up to 2.4 meter block wall and you need to provide sheeting here. Okay. So generally for our steel suppliers will not provide any support to the block wall. Understand? Steel suppliers will not provide any support to the block wall. Okay. So they will provide support for the sheeting only. Right? Understand my point?
Yes, sir.
Right. So what are the supports for the sheeting? If in case walls, we call them as guts. Those are also jet sections, same as purlins, but they will be connected to the walls. Jet sections, those are called guts, GIRTS, guts. Okay. How you have taken this LYUNT UNB support to the rafter? In the same way, you can take LYUNT UNB support to the columns from guts. Okay, but he has mentioned that I need 2.4 meter block wall. So before going to the 2.4 meter block wall, what is the length of this member 2? It is 3.4, right? If you observe clearly, 2.4 comes within the member 2 only, right?
Yes, sir.
So 2.4 comes within the member 2 only. So you can take gut support for member 1. You cannot take for 2 because block wall comes for 2.4. So how you will take? I'll write here. If any doubt, ask me. LY 1.5 members 1 and other side is 3 members 1 and 3. the same thing will be applied for UNT, UNB. So just let me complete this. Just you read this. If any doubt, ask me. LY 2.4 member 2 and 4, right? 2, 4. So I have written like this. So does anyone have any doubt why I have written like this? If you observe the structure, just let me know. You have any doubts? Because the block wall comes under only 2 and 4 members only. It will not come until 1 and 3 members. So guts will be supported to 1 and 3 column members. That is why I have taken gut spacing for 1 and 3. But if you observe here, okay, block wall will come up to 2.4 meter. Over that gut will come. So what is the length here? If you observe here, what is the length here? 3.4 it is, right? 3.4. So 2.4 up to there will be one block wall. So what is the remaining length? 1 meter. So you'll provide gut at 2.4 meter. That is no problem. So over the gut you will have 1 meter length. Below the gut you will have 2.4. Whichever is what is critical one? Unsupported length.
2.4.
Yes, that is why I have taken 2.4. You guys clear?
Yes, sir.
Fine, fine. Thank you. And the other thing is that it is BC column. Okay. The last thing I have remained here is internal column. I can say BC column. You can say anything. Okay. Internal column. You need not to mention LZ because I have not done segments here. If you do not mention anything, it will take entire length. Okay, I have mentioned LZ because I have segmented the entire column into number of parts. You got my point? All these, yes, I'll tell you. I have mentioned LZ here for columns. I have mentioned LZ here for rafters, right? Why I have mentioned LZ? I have segmented all these things, but they should act at a stretch, like they should act as a single member, right?
Yes, sir. Yes, sir.
That is why I have mentioned LZ here. LZ for columns also. I have divided into 2 segments. That is why I have mentioned LZ. But if you observe column 5, I have not divided into segments. If you do not mention anything here, it will take entire length as LZ. So no need to mention LZ, right?
Oh, okay.
Mentioning also no problem. That will not affect. What is LZ? 9.115, right? I can say 9.2, round figure. Member 5. This mentioning also, it will not affect. Okay, but if you do not give also, no problem at all. That is increase your time. If you give all these things, it will increase your time. So that is why you can skip this step. But you have to mention KZ. Okay, whether it is pinned at the top or fixed at the top based on your condition. So you can do it in 2 ways. Okay, if the sway is controlling by own. Okay, if the sway is within the limit, after the design you'll get to know all these things. If the sway is within the limit, you can pin at the top. Okay, if the sway is not controlling, the structure is deforming heavily, you have to fix this point. My point is clear?
No, sir.
No, I'll tell you again. Anyway, we are providing pinned base at the bottom for all the columns, right?
Okay, sir.
So you have to check with pinned connection here also. Top also you have to take pinned.
Okay.
If the sway is in control after the design, you can make like that. top also pinned, because connection will be economical, right? Fixed connection makes you uneconomical most of the times, right? So connection makes you economical. If you pin it also sway is passing, why to go for fixed base? Why to go for pinned connection?
It's not allow movement.
Sorry?
Pinned base is not allow the movement.
No, pinned base will not allow the movement. I'm asking about at the top. It has closed. It has closed. Just a minute. Okay, fine. So pinned base, if you observe here, it has come now. Fixed base here. Fixed base is pinned base is here. If you pin at the top also sway is controlling, then it is okay. If sway is not controlling, you have to go for fixed connection here. Okay. Suppose first of all, I will check with pinned connection. So pinned connection, how they will pin, how you will get pinned connection in the stat, I'll tell you. So before going to that, let me check unsupported lengths here. So what is the KZ value for, sorry, what is this? Okay. So this is the condition, right? Base is pinned, top I will release now. Okay, top I will release. So if both connections are pinned, what is the KZ value here?
1.
KZ value 1. That is why I can mention KZ value 1. Member, what is the member number here? 5. So member 5. Okay. Because it is 1, no need to mention this one also. You can skip this step also. If it is other than 1, 0.85, or if it is 1.2 or 1.5 or 2, anything you have to mention. Since it is 1, no need to give, right? 9.2 into 1, how much it will be? 9.2 only. Anyway, 9.2 only you are not giving. If you are giving also, no problem at all, I will tell you. Okay. And any support comes to this internal column? No, right? Sheeting will be all around the building. There will not be any internally something. If any customer wants partition, that is other thing. If customer does not, yes, tell me.
Sir, if it is any crane, something is coming, that time we divided the column.
Yes, of course. Yes, of course. We can take unsupported length up to crane beam.
Okay.
Okay. How it will be, I'll tell you. How it will be, I'll tell you. Yeah, tell me.
Any bracing, anything?
Bracing support you cannot take here.
Okay.
Bracing support, you will not, you should not take any bracing support to the here. If any strut coming in between, that is the other thing. Ly you can divide. Suppose if the customer wants economical design, some customers will allow you to run struts along the longitudinal direction. Okay, since it is 9.2 meters, some customers will tell you that please provide strut at the middle portion of the internal column so that unbuckled length will, buckling length of the column will be reduced. Okay, suppose in this case, generally what will be Ly? 9.2, right? Because you are not giving any support at all. There will not be any sheeting support, anything, right? Ly UNB will be full length, right? But if you provide strut here, Ly you can break middle one. Okay, whatever the height you are providing strut, you can give that to Ly. My point is clear?
Clear, sir.
Fine. Because in this is the simple design, I'm not providing any strut here. Yeah, yes, tell me.
Clear.
Clear, huh? Okay, fine.
Why we are not LX?
Huh?
Portional.
Yeah, exactly why we are not providing LX. Yeah, I'll show you. This is the cross section, right? LX providing also, there will not be any problem. Okay, providing LX is not a problem. Whatever the LY you are giving, that will be comes under LX. But instead of LX, we are giving UNT and UNB. Okay, I told you purlin will run over the rafter, right? Like this. So purlin will run like this. If you see cross section, purlin will run like this. The flange bracing support will come to beam like this. Diagonally.
Some instance they are skipping the flange bracing, alternately they are using.
Yes, in that case, that is very good question. In that case, top length will be 1.5, right? Anyway, top of purlin will be connected directly to the rafter.
Yes, sir.
The remaining two portions alternatively, you told me, alternatively 1.5 into 2. Like this, you have to give.
Yes, sir.
Clear?
Yes.
Sorry, sir, I am not getting this question exactly.
Okay.
He's asking. What is he asking?
What is he asking? You are not getting. Yes. Just let me draw one thing. How I can draw? Okay. Okay. Anyway, I'll draw one cross section here before going to that. So this is the I section, rafter section. Suppose member 12 here. Okay.
Okay.
So purlin will run. Sorry, my drawing is not proper. Please don't think anything. Okay, purlin will run longitudinally above the rafter.
Okay.
Okay, so here in order to provide bottom, in order to provide support to the bottom flange, there will be flange bracings like this. Okay.
Yes. Yeah.
These are called flange bracings. Okay. But some suppliers, some steel providers will provide these flange bracings alternatively. Suppose if there is one purlin here, one purlin over here, one purlin over here. If he provide one flange bracing to the rafter for this purlin, he will not provide to the next one, and he will provide alternate one.
But this flange bracing is required for everywhere, sir. There are no need.
No, not necessary. Not necessary. Okay, that is just flange bracing is just to reduce the unsupported length of the bottom flange and web.
Okay.
Clear?
It means the section coming economical if you go.
Yes, yes. If you give everything, the section may come economical, but I can say there will not be much change.
Wow.
There will not be much change because 1.5 and 3 are very much similar in the design. Okay, there will not be much change. If you do one thing, just take the same frame, do 1.5 for all these things, and take alternative things also. Just try. If there is any change in design, it matters. But there will not be any change in design. There will not be even change in 0.01 ratio also. Okay, that will not govern that much. Okay, but if it is more, if it is 5 meters like that, it will govern. But these two are not much govern. Okay. So this is all about giving unsupported lengths. Just I'm closing this thing. So if you click Control 1, if you click Control 1, it will show you the outline of the structure. Okay. Otherwise, Control 0, it will again show the center line. Control 2, it will show the solid structure. Here, Control 1 is for outline. It will be like transparent. If you want to show the solid structure, how it looks like, if you click Control 2, it will show the solid structure. Clear? These are the comments because it will be helpful. If you see here, I have told yesterday, you have to give flat bottom here. If you observe in the front view, it is not coming actually flat bottom because STAD is taking center line here. But roof slope will be 1 in 10. You have to maintain roof slope will be 1 in 10. The actual member will get downward here in this direction so that it will get flat bottom here. That is in actual case. That is the actual case. Control 0. It will again get center line diagram. So this is how you have to take all these things. Yes, one thing I forgot again. This thing, after giving all these things, one thing you have to mention, you have given one code here, but you have not assigned to the members. You have to assign code to all the members. That is by using check code option. Check code for all members. Check code all. This is for assigning of the code. Like in the stat, what you have defined is other thing, whether it is assigned or not. That is the important thing. Check code is the assignment of code to the members. Okay. Now I'm going to change units, meters, and kgs, because the final weight you have to give to the customer is in tons, right? There will not be any tons in the stat pro. That is why maximum weight we can give up to kgs. That is why I'm changing the units to meters and kgs. Steel takeoff. The next command is steel takeoff. With this command only, you can obtain the steel weight of the entire structure. What you have defined in the, what you have provided in the geometry. Okay, steel takeoff all the members. Sometimes you can take member 1 to 23 or 1 to 20, 1 to 14 only, anything you can take. But I need all the members, right? That is why I'm mentioning all. Okay. This is a complete analysis and design of structure. If you click Control F5, it is asking one or more empty load cases are detected in the model. Do you want to run the analysis? Where we have mentioned empty load case? Do you guys remember?
Mezzanine and
yes, exactly. Mezzanine. Mezzanine only. We have not given any load case in the mezzanine. It is dummy load case because I have mentioned in the combinations. That's why I have written like that. It is the dummy. Okay. So it will not affect my design. So I'm clicking yes. So you can see 0 errors, 0 warnings, 0 nodes. Everything is perfect and according to the code. If you click right click, structure diagrams, design results, show diagram, it will show you the thing. Okay. So this is how you will get, you'll design a rigid frame. Okay. How to optimize and how to pass all these things, I'll let you know in the next class. So it is clear now, all these things, right?
Clear, sir.
Thank you. Thank you very much for your joining. Sorry for the late. Okay.
No issues.
No problem.
Okay. Sorry for the late. Actually, I have taken much more time because I have to explain everything, right? You guys should take it in your minds. That's why I have taken much more time to explain you. Okay. Sorry for the late again. Okay. Thank you very much, one and all. Do practice. And if you have any doubts, please note it down and ask me in the next class.
Okay, sir.
Thank you, one and all. Bye, one and all. Thank you. Thank you. Bye.